And right shift 1 and 1. And I also say provide you with the fact that n is always less than or equal to 10 to the power of 9. So how do you count then? Mm-hmm. Ritvik, would that really work? I mean, check for this case only, no? I want you to return 3, right? Yeah. So what loop would you use there? What loop? Take 2 minutes to like completely understand the question and figure out what way works. Anyone else with the approaches? While n equals 0, correct or not? Doesn't seem to be right to me. Hmm. It is still wrong, Ritvik. No, Pavitra, that would not work. Okay, when all right, Pavitra, that might work. Yeah. Yeah, I see a lot of correct approaches in the chat. It's nice. Right. So let's quickly discuss the approach. So, of course, there are like multiple ways to do this problem. That would fail, Ritik. and Pawan as well. There is a, like a very simple mistake, a very small mistake. Fine, let's just discuss the approach. Right. So let's discuss approach number one first. Now, yeah, let's take this number 101000. Okay, let's set this one. Right. So we need to basically return 3 as our count. Right. So we know for a fact that all zeros are padded over here in here, right? So our task is basically, now what I will do is I will bring every single bit down to this last bit and check if it is 1 or not. If it is 1, then I will increase the count. If it's not 1, then I will just right shift the number by 1. Right. So we will just go bit by bit, checking if it is 1 or not. Right. So first, what we do is we check if the last bit is 1 or not. No. Right. So the count, I'll initialize the count to 0. The number is basically 101100. Right. The last bit is unset. So I will not increase the count, and I will move forward by right shifting the number by 1. I will bring the next bit, the previous bit, down to the last bit. So 1011 becomes the number, and my count still remains 0. And even after doing this, my count still remains 0 because the last bit is unset. Now what I will do is I will bring the previous bit down to the last bit again, and this time my count becomes 1 because the number is 1011, and this bit in this particular bit is set. And you know how to check if that particular bit is set or not. You AND it by 1. That's all. I guess that is clear enough, right? So the count is 1 now, right? So now the next thing, what I will do is, now that I'm done with this bit, I will eliminate this bit and I will bring the previous bit down to the last one. So the number becomes 101 and my count becomes 2 because the last bit is set here. Now moving down to the next bit, I will bring the previous bit down to the last bit, and then my count still remains to 2 because this bit is still unset, right? Now I will bring this bit down to the last bit. The number becomes 1 and my count becomes 3, right? And I will basically end it over here, right? I will just probably just move this bit to the last bit and become 0. And when the entire number becomes 0, I will end my process. Right. So I return the count as 3. So it all boils down to the same thing. Whatever you want to check, whatever it is that you want to check, you bring it to the last so that things basically become easy for you. Right. So now on paper this looks very cool, right? So how do you exactly put it to the code, right? So now what I'm doing is I am continuing this entire process until my number, whatever is given to me, does not become 0, right? So what I will do is I will run a while loop while n is not equal to 0. I will initialize the count variable here to 0. So what I will do is I will check if the last bit is set or not. If the current last bit is set, if n and 1 is equal to 1, so this just means that the last bit in my number is set. Okay, so I will say count plus plus, or else I will just basically do nothing. And for every iteration, what I will do, I will right shift the number by 1. N is equal to n right shift 1. That's all. When the while loop ends, you print count. This works. And nice to see you people have answered it correctly. While n right shift 2. While n left shift 1. No, Ritvik, I guess that would not work. Basically, we are repeating this entire process until n becomes 0, right? You are bringing every single bit down to the last bit, and then you are basically when the number becomes 0, there is literally no point checking for set bits, right? The entire number, if I have I'm done with all of these numbers, and I am done. So the entire thing which is left here is zero only, right? So when n becomes zero, the entire thing, we just stop the entire process. So that's that. Give me a thumbs up if you guys understood this, or shall I explain it more deeply? If you guys have any doubts, please post it in the chat, or give me a thumbs down so that I know that you have a doubt. Cool. Okay. I Now let's move on to the next approach. Okay. So now I explicitly mentioned to you that n left shift 10 to the sorry, n is less than or equal to 10 to the power of 9. So now, how many maximum bits can 10 to the power of 9 have set? Up to 10 to the power of 9, how many max bits can be set? Anyone? What is the maximum number of bits that can be set for any number up to 10 to the power of 9? Provided the fact that it is approximately equal to 2 to the power of 31. 31. I will repeat myself again. What is the maximum number of bits that can be set for any number up to 10 to the power of 9? If the question is not clear, please give me a thumbs down. 50 into 16. Let's not go with that, like for the plus or minus for now. Okay. Yeah. So now, so how we know for a fact that like the number okay, it's maybe n is less than or equal to integer max. Let's say, let's call it integer max for now. Okay. So like say, let's look at 2 to the power of 1. Right. What is 2 to the power of 1? It's basically 1 0. Yeah. 2 to the power of 1 is basically 1 0. And if I call 2 to the power of 31, like there are basically 2 bits over here. Let's say we are looking at 2 to the power of 31. right? So if we have 2 to the power of 31, we have some basically 32 bits over here. And I can say that 2 to the power of 31 minus 1 is the maximum integer limit, and this will basically have this number unset and all these numbers set. 32 bits, right? Yeah. This entire thing is like 32 bits, and this number is unset. All these numbers are set in 2 to the power of 31 minus 1. So the number of maximum bits that can be set in an integer is 31 bits. No more than 32 bits can be set in an integer. When I give you an integer, say only 31 bits can be set, and no more than 31 bits can be set in an integer, right? So now I have an upper bound on the number of bits that can be set. The number of bits cannot, the number of set bits cannot exceed this particular number when I give you an integer, right? Which is approximately like say let's call it 10 power 9. Okay, right? So now what I can do is I can iterate on all these 31 bits, right? So for int I equals 0, I equals 0, I less than 32, I plus plus, what I will do is I will check for every bit, like whatever the number is given to me, 10101110, whatever that is, I will bring the ith bit down to the last bit and check if it is set or not. Count is 0 initially. For I equals 0, I less than 32, I plus plus. If n right shift I, uh, if n right shift I and 1 is equal to 1, I will say count plus plus. That's all. That is it. Right. So it all basically works on the fact that there can only be 31 bits set in a particular number. So I will iterate from I equals 0 to I less than 32, I plus plus, and say if n right shift I and 1, count plus plus. That should work. And this will only work if n is up to 10 to the power of 9. What if I say that n is up to 10 to the power of 18? What will I have to do differently over here then in this approach? What would I have to change? I would have to change only one single value over here, and this thing would work. What is that number? I. So what do you think? If I change this I to j, will it work? 32 to 64. Cool, cool. Correct, 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 correct. Yeah, yeah, nice. Yeah. So when I give the number up to 2 to the power 10 to the power of 18, this is approximately equal to 2 to the power of 63, right? So it can basically have like 60 2 bits set at max. So I can just put less than 63 over here, and that would work for 10 to the power of 18. So for any general number, you can just say like, or rather by not using this, you can just go with this approach to count the set bits, this while loop approach. This will work nonetheless if this works even if n is 10 to the power of 9, or this even works if n is 10 to the power of 18. It works both ways, right? This is a general approach, and this is more of a, yeah, this is more of a rather specific approach as to how to count the number of set bits. Okay, so if this is clear, I'll move on to the next thing. Give me a thumbs up if everything what I just said so far is clear. Okay, thank you very much. Okay, another question. I will give you a number n, and I want you to figure out if this number is a perfect power of 2. Now, can this number be represented as 2 to the power of k? Is my question. Give me a thumbs down if you did not understand the question. If given a number, can it be represented as 2 to the power of k? For 16, it is a yes, because it can be represented as 2 to the power of 4. And for any other number, like say 28, this it is a no, because it cannot be represented as 2 to the power of something. So your task is to check. Mm, right shift k equals 0. I am not giving you any k. I'm not giving you any k, by the way. I'm so sorry. I am just giving you n. And if I want you to check if the number can be represented as 2 to the power of k. For 16 it is true, and for 128 also it is true, because it can be represented as 2 to the power of 7. I will only give you this 128 and nothing else, basically. I want you to figure out if the number can be represented as a 2 power. Hmm. Okay, good, nice. Just two people. Also, oh yeah, well, of course, the answer is correct, Karthik and Ritvik. Can you think of anything else, something better? And also, can you guys tell me what is the time complexity of finding the number of set bits? Like you told me that you find the number of set bits and you count the number of set bits, and if it's equals to 1, you say that the number is a power of 2. So, what is the approximate complexity of that approach? Say if the number is up to if n is up to 10 to the power of 18, what is the complexity of finding the number of set bits? Yeah, okay. Yeah, the code and all is cool, but then what is the complexity of that? What is the complexity of that snippet? Order of n, huh? Are you sure, Amog? Hmm. Well, yeah, order of one. Okay. Meanwhile, think of another approach how to solve it. There is another simpler. Hmm. Oh, we have a winner. Any other approaches, people? Uh, I've seen Nihesh, Answer, Pavan, Navdeep, Jahnavi, Devendra, Pavitra, Taruni. Any other approaches, you people? I mean, it's fine even it's wrong. What is the worst that could happen? Hmm. Okay. Fine, let's get down to it. Now, obviously, we've seen how to count the number of set bits in a particular number, and we know for a fact that 2 to the power of k, any number which can be represented in the form of 2 to the power of k, has only one particular bit set in its binary representation. It's all zeros, and then the kth bit is set, and then there's all zeros. right? So this is how 2 to the power of k looks. There's all zeros, there's a 1, and then there's all zeros in the k, and the kth bit is set, right? So now we used like we know how to count the number of set bits in a particular number. We've learned it so far, right? So we count the number, like we count the number of set bits in a particular number given n, and if the count is basically equal to 1, the number is a 2 to perfect power of 2, or else it is not. As simple as that. Now what this does is this basically requires you to iterate over the number of bits of a number. So it's basically order of 64. We can of course generalize it to O of 1, of course, but then there is a very nice approach that you can deal with. Like instead of iterating over all bits, you can find out the number. You can find out if the number is a perfect power of 2 or not in a like a single line, right? So now let's look at this number. Let's this interesting number called 1111. Okay. So in binary, of course, this number. Hmm. Yeah, Ritik, correct, correct. That is correct. Yeah. So this is the particular number that we're given. Okay. So now what I'll do is I'll add 1 to this number, and I hope you all know how binary addition works. So how binary addition works is almost like similar. Like 1 and 1 gets added to 0, and then the 1 is basically carried over here. Again, 1 and 1 is added, 0 here, 1 is carried over, 0, 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 and then 1 is carried over here, and then 1 is put over here. That's all. Right. So you do you realize the fact that when I have a number in which all the particular bits are set, and if I add 1 to that particular number, that number basically turns out to be a complete power of 2. Make sense? Give me a thumbs up if this makes sense. This is like basic binary addition. When I take a number in which all the bits are set, and if I add 1 to that particular bit, the one all zeros are padded over here, and the entire one is carried out. Like the one is carried out, and this becomes a perfect power of 2. Only one particular bit will be set in that number. Okay. So now I can safely say that if my number is 2 to the my number 2 to the power of k, if it looks like this 1 0 0 0 something like this, say let's call it 2 to the power of 3, my number 2 to the power of 3 looks like this, I can say that 2 to the power of 3 minus 1, it looks like 0 1 1 1. They are both complementary to each other. Same goes with this thing. If a number can be represented as 2 to the power of k, I can say that there are k zeros over here. All these are k zeros, and I can say that 2 to the power of k minus 1. Mind you that it's not 2 to the power of k minus 1, it's 2 to the power of k minus 1, right? So if, when I say 2 to the power of k minus 1, the number will just basically turn out to be this 1 becomes a 0, and then all these k bits will be turned to 1. Make sense? Make sense? Give me a thumbs up if this makes sense, please. Thank you. Thank you very much. Right. And if now that you look at this, if I complement this, if I and both of these numbers, I know for a fact that no number matches. Not a single number matches in this particular in this entire thing. And I know for a fact that and will only return 1 if both the numbers are 1 and 1. Like 1 and 1 only returns 1. In any other case, the answer is 0. So now if I and both of these numbers, if I bitwise and both of these numbers, every single complement number will become 0. 0 0 0 0 0, everything will become 0. So the entire number will turn out to be 0. So the easiest way to check if a number is perfect power of 2 is like if I give you an n, and if I ask you if it is a perfect power of 2, you say if n bitwise and n minus 1 equals 0, the number is a perfect power of 2, or else the number is not a perfect power of 2. Cool, make sense? Give me a thumbs up if you guys understood this. This is going to be very like important. Well, all right. Hmm. So this basically marks the end of bit manipulation. Right. So now, whatever I've told you so far, like how to count the number of bits, how to check if the number, if the bit is set or not, we use this basically in every bit manipulation, almost every bit manipulation question that we tackle. Right. So this is like very important to understand, understand these facts and remember these facts. Right. And also, I cannot stress enough with the fact that whenever a question on bit manipulation is given, whenever you see these numbers called, well, this is blindly follow this. Okay. Whenever you see words called bitwise and bitwise or bitwise zor in your questions, whatever is the whatever the question may be, now if you really want to solve that question, if you want to really tackle that question, you need to look at the binary representation of the numbers. Right. If you do not look at the binary representation of the numbers and you only work with decimals like 10, 9, what is 10s or 9, what is 10 or 9, whatever like that. If you work on the if you do not work on the binary representation of the numbers and if you only look at the decimal part of it, you are not going to get to the answer. Never or ever are you going to get to the answer. It is going to be confusing as hell. Right. So whenever a question on bit manipulation is given, please visualize these decimals in the form of bits. Work on bits and bits only. Do not go to these decimals. Do not work on decimals. If a question on bit manipulation comes, you can blindly follow this and you can solve any bit manipulation question on earth. Any and like even the hardest of the hardest questions, they only look at how well you're able to visualize the binary bits of a given decimal number. Right. So that is it from bit manipulation. So if you guys have any doubts, please post it in the chat box. I'll give you 2 minutes. We'll start off the next topic at like 10, 10 or 10, 11. Sorry, 11, 10 or 11, 11. I'll basically open the chat for questions. And also, please revisit the questions that you have not been able to solve in bit manipulation, the previous questions which you're not able to solve, and see if you can tackle those questions with this particular approach, like visualizing the number based on bits. Like based on our experiences, I can definitely tell you that any bit manipulation question can be done by visualizing the number correctly in form of bits. Okay, since there are no questions, I will move on to the next topic. I will not be covering number theory in depth, of course, but then let's just look at some very trivial problems. Right. So I give you a number n. I want you to count the number of divisors of n. I hope you all know what divisors are. If I take 12, the divisors of 12 are 1, 2, 3, 4, 6, and 12. So what I want you to do is I want you to count the number of divisors. This is I guess this is like very trivial. You guys like would have solved it in like first year or so. I mean for one also in your C lab, data structures lab, whatever. If I can quickly get a response, we can move on fast. This is like a very basic question. So how do we do this? How do we go on about doing this? How do we find the number of devices of a number? Yeah. Okay, it's trivial. We'll just continue. Right. So we know for a fact that all the devices, they lie in the range of 1 to n only. You cannot find a divisor of a number n after n. Right. You can't find a divisor of 12 after 12. You can't find for a divisor like after the number. Right. So it's basically just a simple for loop for I equals 1 to n. If n mod I equals 0, I can say that I is a divisor of n, and count plus plus, you output the count later. Nothing fancy, very simple. What is the time complexity of this approach? Order of n. Can anyone tell me how to do better? Of course, I don't want order of n, right? If I give you a number which is n less than or equal to 10 to the power of 9, would this thing work? Yeah. So, correct. Yeah. So, can we do any better? I want answers for n less than or equal to 10 to the power of 9. Any approach that works for 10 n less than or equal to 10 to the power of 9. Okay, Lasya says square root of n. How, Lasya? Can you please explain? A brief explanation would do. Okay. All the devices are bound to be less than square root of n. Are they? Now, I mean, of course there is a like square root of what is square root of 12? Square root of 12 is approximately 3 point something. But divisors 4, 6, 12 are greater than square root and they are not bound to be less than square root. Right? All the divisors are not bound to be less than square root of n. That is like very trivial that we can observe in 12 also. Then how is it like square root of n? Yes, correct. Yeah. Hmm. So let us like quickly discuss the approach. Right. So now I asked you about 12. Let's look at 12 only once. Now, if I say 1 is divisible by 12, is 12 by 1 also divisible by 12? In a way, I am basically telling you that if one is divisible by 12, can I call 12 by 1 also divisible by 12? And if 2 is divisible by 12, can I say 12 by 2 is also divisible by 12? And when 3 is divisible by 12, can I say 12 by 3, which is 4, is also divisible by 12? Let's take another example. I have 24. Now, I know for a fact that 1 is definitely divisible by 24. Then I can also say that 24 by 1 is also divisible by 24. 2 is divisible by 24. So 24 over 2, which is 12, is also divisible by 24. 3 is divisible by 24. So 24 over 3, which is 8, which is also divisible by 24. If I say 4 is divisible by 24, 24 over 4, which is 6, is also divisible by 24. And I can say that there are no other divisors for 24 other than these 8: 124, 212, 38, and 46. Now, if I see, I only went till 4, and I somehow almost got all my divisors, right? Even if I went to 6, okay, if I say I say 6 is a multiple, sorry, divisor of 24, and say 24 over 6, 4, which is also divisor of 24, I would be recounting this pair, right? 6 4 6 is already done. I do not have to count 6 4 again. Now, if you see, I am only going till 4. I only went till 4. Let us understand why is that. Okay, let's assume a big number line. Okay, here is 1 and here is n. Now, at least now, we've deduced the fact that is everyone okay with the fact that if I is divisible, then n by I is also divisible? Yes or no? Give me a thumbs up if that's okay. Or shall I explain it more in depth? Cool. So if I is divisible, then n by I is almost, of course, divisible. Let us say I have my I over here and I have my n by I over here. Let's call it I1. If I have my I2 over here, I will have my n by I2 over here. If I have my I3 over here, I will have my n by I3 over here. Is that fine? Now, okay, let's, in the case of 1 and 24, if I have my 1 over here, I have my 24 over here. If I have my 2 over here, I have 12 over here. If I have 3 over here, I have 8 over here. If I have 4 over here, I have 6 over here. And that is where basically I stop. Now, now if you see, when exactly did I stop? I stopped when this I and n by I are too damn close to each other, right? So I basically stop my process when I is approximately equal to n to the n by I. Yes, Pavitra, that is correct. So when I is approximately equal to n by I can cross multiply this, and I square is approximately equal to n. I is approximately equal to square root of n. Cool. So whatever counting it is that I was doing over here, I can only keep it down to root n. I can only go down to root n, and I can get all the divisors possible for that particular number. Is everyone okay with this fact? I do not have to go until n to count all the divisors. I can only go up to root n. I can only go up to root n and then count all the number of divisors. If I is say a divisor, then n by I is also a divisor. Okay, cool. Give me a thumbs up if you guys understood this, and a thumbs down if you have not, so that I can explain again. Okay, Rishi. Hmm. Yeah. So, so what happened over here is Rishi, did you understand the fact that n by if I is a multiple of n and then n by I is also a multiple of n? Did you understand this fact? Yeah. So now if I carefully look at this number, this particular number line, one is multiple of 24. Sorry, one is a multiple of 24. So I can say that 24 over one is also multiple of 24. Right. I'll write it on new line. So if one is multiple of 24, I can say that 24 over one is also multiple of 24. If 2 is multiple of 24, I can say that 24 over 2 is also multiple of 24. If 3 is a multiple of 24, I can say that 24 over 3 is also multiple of 24. If 4 is a multiple of 24, then I can say that 24 over 4 is also multiple of 24. Right. Now, if like, do I have to check for 6 also? Like if I go and check on for 6, okay. Like if 6 is a multiple of 24, I can say that 24 over 6, which is 4, is also multiple of 24, right? But we also deduce the fact that 4 is a multiple of 24, right? We need not check this again. Like we need not come down to 6 and check 4 again. So the question is, now I know I knew to stop here at 4, right? I knew that I should stop here at 4 and stop my checking so that all the devices are done. Like I have counted all the devices and it's and my process is done. Now the question is, now by the looks of it, I could say that I need to stop at 4 because I'm recounting, right? But how do you like explain the machine how to do it? Machine can't think of its own, no. Machine can't be like, okay, I've counted this pair already, I do not have to count that pair already again, right? So you have to teach the machine how to do it, and you have to tell the machine you need to stop somewhere. We need to stop checking somewhere, right? Now what exactly that is that point? Now if you basically the reason why I drew a number line is to visualize it to you how to stop checking, right? Now now look at this particular number line. I have 1 and I have n. I have I1, which is a divisor of n, and I have an n by I1, I2 n by I2, I3 n by I3. Now there comes a very slight point where my I lies over here and my n by I lies over here, right? And this is somewhere that I do not want to go. I do not want my I to be greater than n by I. This I do not want, because if I do that, I will be recounting the pairs. Like in the case of 24, where 6 turned out to be greater than 24 by 4. Sorry, my bad. Where 6 turned out to be greater than 24 by 6. This I do not want. When this happens, overcounting happens. So I can safely say that I is always less than or equal to n by I. I square is always less than or equal to n, and I is always less than or equal to square root of n. Okay, you only have to check your divisors up to square root of n to find all the divisors which are on the right side of right part of it. Now, did you get it? Yeah, thanks, Rishi. Yeah, so that's that. Now, how do you basically put this in code? So for int, now I will basically say my count is equal to 0. For int I equals 1, I less than or equal to square root of n, I plus plus. Now I can say if n mod I equals 0, then I say that I is definitely a multiple, yeah, definitely a divisor of n. So I can say count, like what I will do is I can say count plus equal to 2, no? Because n by I is also a divisor of n. Sorry, n by I is also a divisor of n, yeah. That's all, print count. Cool. Does everyone agree with this? Yes, nice catch. Right. So let us look at 36 now. For 36, I have 1. So 36 by 1 is also a divisor. I have 2. 36 by 2, which is 18, is also a divisor. I have 3. So 36 by 3, which is 12, is also a divisor. I have 4. 36 by 4, which is 9, is also a divisor. Now, if I have 6, 36 by 6, 6 is also a divisor, but I do not have to increase the count twice. Because 6 is already counted here, I do not have to count 6 twice again. Okay, so when the number is a perfect square, I do not have to count it twice, but I only have to count it once. So the change that I want to do to this particular code is, if n mod I equals 0, I will check if n by I equals I will say count plus equal to 1 because I do not want to recount. Else count plus equal to 2. That's all. And then print count. Is everyone okay with this? Please give me a thumbs up if you are. Okay, thank you. Now, I'll give you another question. Given n, I want you to find if n is a prime or not. How do you go about solving this? Number of devices count equals 2. Correct, correct. That would work. Ramya, like, okay. Nice. So what is the complexity now? Like, okay, yeah. What is basically what is the complexity of counting the number of devices of a number now? It becomes order of square root of n because we are only traversing from 1 to square root of n. Correct. Yeah. Same as previous, but after getting a first divisor rather than one break, not prime. Cool. Yes, that works. Correct. Hmm. Yeah. So, well, you guys know for a fact that prime numbers have only 2 divisors, right? It's 1 and basically itself. If I have 7, the divisors of 7 are 1 and 7 itself. There are no other divisors. So, yeah, one way that could work is like you count the number of divisors, and then if count is equal to 2, then you say that number is a prime. If count is not equal to 2, the number is not a prime. Hmm. So Devendra, yeah, that will work, Devendra, but the complexity of that is like order of n. We've already learned that we can count the divisors in square root of n. Count the number of devices in square root of n, and then yeah. Hmm. But the point that I want you to understand over here, like one approach, that approach works. But then the point that I want you to understand over here, like let me just tell you the fundamental theorem of arithmetic. Now I can say that when I give you a number n, I can always express these numbers in the in its unique prime factorization, right? So I can have n1 as p1 to the power of x to p to the power of y to p3 to the power of z, something like that. Right. The fundamental theorem of arithmetic states that every number has a unique set of prime factorization associated with it. If I have 24, it has a unique prime factorization. It has like 2 cube times 3. This is its prime factorization. If I have uh, oh, give me a number. Um, if I have 17, it basically has only one prime factor, which is 17. 17, that is the prime factorization of this number. And if I have say 15, 15 has basically 3 into 5 as its prime factorization. So fundamental theorem of arithmetic states that every single number, every single real number has its own unique prime factorization, right? So now I basically deduce the fact that I can represent this number as a power of primes, right? Is p1 to the power of x1 to p to the power p2 to the power of x2 to something, right? So the next thing is I instead of like going from what we did in first year is we went from for I is equal to 1, I less than n, I less than equal to whatever, I plus plus. Like if any number other than 2, if any number other than n is divisible by this particular number n mod I is equal, if n mod I is equal to 0, then you break and you say that the number is not prime. And if n mod I is not equal to 0 anywhere, then you say that the number is particularly a prime. Now, what if I told you that you only have to go up to square root of n? You do not even have to go up to n. You can uh, only go up to square root of n. Now, can anyone prove it to me? Why is this fact correct? Why do I only have to go up to square root of n? I've seen people say that Karthik say that for int I equals to I square less than n I plus plus. But why exactly do I only have to go till square root of n? Knowing why it works is not the way to learn. Knowing the proof is the way to learn. Like if you know the proof, you will just remember it. Like that will just sit in your mind. If there are no devices below root n, there are no devices after root n. Very good, nice, good catch, Nihesh. Yeah, so that thing works. Now, what Nihesh says is, if there is if there are no devices below root n, there are no devices after root n. That is all. That also works, and that is like basically very trivial after what I explained to you about devices. Now, now, I say that okay. I'll ask you this question: how many distinct prime factors, and also these numbers, whatever p1, p2, p3, which are there, these are called the prime factors of a number. Okay, this is basically elementary mathematics. I don't have to tell you that, but then I'll mention it anyway. These numbers, whatever p1, p2, p3, these are all called prime factors of a number, right? So now tell me. My question is: given n, sorry, given n, and if I tell you this n is always a prime, okay, n is always a prime. How many maximum number of prime factors can this number have? N? Yes, yes, correct, correct, correct. Yeah. Hmm. So the thing is, now, if I say let's go back to the previous question and say and try to figure out if the number n is a prime or not. Right now, what I'll do is I'll assume that n is not a prime. Okay, if n is not a prime, then this particular number will have at least two prime factors. Is it correct or not? If the number is not prime, it will have at least two prime factors. Is this fact correct or not? Yeah. So Now I'll try to prove the contrary. Now if like n is if I assume that n is not a prime, then I can say that it can be represented as p1 power x1 into p to the power of x2 at least. Like there are at least two prime factors, right? So for this to happen, what now what I'll do is I will go on up to square root of n, and I'll check if there at least exists one prime factor. Okay. Now, if I have not find if I did not find any prime factor until square root of n, it is always sure that the number is a prime, right? So, like what I'd like to mention over here is there is always at least one prime factor less than or equal to square root of n if the number is not a prime. So if the number is not a prime, there at least exists one prime factor which is less than or equal to square root of n. Okay, and if the number is prime, there of course exists like no prime factor, and the prime factor is basically n itself. Does everyone agree with this? Yes, no, thumbs up, thumbs down. If anyone did not understand, please put a thumbs down so that I can explain it more. So the key point that I want to explain to you guys is there is at least one prime factor less than or one prime factor less than or equal to n if the number is not a prime, and there exists at least like and also there is no prime factor other than n if the number is prime. Okay. So basically there is a proof to this proof as to why this thing works. The time might not permit for me to explain it now. So if you like wait until the end of the session, I'll probably explain it at the end of the session as to why this is true. Okay. So for now, I guess this is basically the elementary number theory. Okay. Whoa, whoa, whoa. Yeah. So this is basically elementary number theory. Okay. Very basic number theory. Um, So if you guys like want to explore more part of number theory, you can go and check C of Eratosthenes. And check out like prime factorization of a number. How do you prime factorize a number? If time would have permitted, I would have explained you at least prime factorization of a number. But then we need to cover more topics now right now. So I'll now hand it over to Manorath. He's going to explain you about frequency arrays. Okay. Take a screenshot of this so that you don't forget. Right. Oh, also, if you guys have any doubts, please post in the chat box about number theory or bit manipulation or whatever.
Yeah. Okay. Before starting off the new topic, I'll just give you a small question. Uh, like, okay, the question is like you are given an array A of size n, and you're also given the constraints that the array has only the elements, the integers, like in the range of 0 and 10. Okay. Now, what I want to output as is I want you to print like all the numbers, like all the integers from 1 to 10, and how many times they occur in this array A. Like you can just give the brute answer for this. You can just post it in the chat. Okay, just give me a brute answer for this question. Yeah. So yeah, for the brute answer, yes, you can just have a for loop which goes from 0 to 10, 0 to 10, and just you have to have a count which you initialize it with 0, and again, yeah, you just go from j 0 to less than n. If the number is equals to count, a of j is I, you increase the count and output it, right? Yeah. So this is a brute approach. Like most of you are saying a map and frequency arrays. Yeah, I don't guess everyone knows. Everyone has an idea about it. So I'm just revising you the concepts like from the brute. Yeah, you can use maps, but coming to maps, you have an extra login time in that. So we'll just use. We'll come to the concept. Like I'll give you an extra constraint where a of I is 0 less than or equals to 10 power 5. How do you do this? Don't use maps. Like give it in C. How do you do it in C? Yeah, you can post it in the chat. Yeah, someone said counting frequencies. Like, how do you do it? Yeah. So for this counting frequencies, how do you count these frequencies? That you have an array. Yeah, you take an array like int a, like frequency array, 10 power 5. Yeah, and you initialize everything to 0. And then you loop over this array from 0. Yeah, okay, you loop over this array, like you loop over the array from 0 to n. Then what do you do is you use this frequency array to increase the count of this number in this, like the frequency. We get this frequency from this frequency array. So what is this frequency array? Can anybody say what this is frequency array? Okay, if you're understanding this, whatever I said, you have any doubts, you can just hands thumbs up or thumbs down. Okay. So what is this free? What? Yeah. So how this frequency array works is, it's just like an key value pair. Yeah, key value pair where the key here is the index and the value here is the count of this number that we are counting. Yeah. Okay. So how many of you understood like using this constraint from 0 to 10, 0 to a of I, like less than or equals 10 power 5? How do you use this? How do you count the frequency of this numbers in an array? If you have understood that, you can just thumbs up or thumbs down. Yeah. Now I'll say that I have an array which consists of numbers from minus 10 power 5 to a of 10 power 5. Now how do you do this? Because index can't be negative. So how are you going to handle this case? Yeah. If you have the answer, you can just keep it in the chat. Okay. Did you understand the question what I gave you right now? If you didn't understand, yes, you can do a thumbs down. If yes, a thumbs up. Okay. So how do you handle this case where you have negative numbers in this array? No. So what I'm giving here is that you're given an array which consists of even negative numbers. But how do you count the number of like the frequency of these negative numbers in this array? Because I just, if I is less than 0, I didn't get you. I, yeah, how do you handle this case of I is less than, like if the number is less than 0, you don't have an index where you can store that, right? Where you can store this negative numbers. So in this case, what do you do is you can just add this 10 power 5 to the number so that it becomes positive, right? Did you understand this? If yes, you can have thumbs up. Yeah, that's correct. So you can just add that number to this frequency, like not I plus 10 power a of I plus 10 power 5 plus. Because let's say if you have an array like minus 10 power 5 and 1 0 10 power 5, just can't like know the frequency of this minus 10 power 5 because there's no index, no negative index. So what do you do is like a of I, like it's a of 0 plus 10 power 5 plus. Not if I less than 0. Just have to do it for every number. Did you get that? If yes, a thumbs up. Okay. So again, what you're doing is here, you're counting the frequency of these numbers, right? I'll give you an array like example -2, -3, then 0, 1, 2, 4. Okay. So what you do here is you're doing frequency of -2 plus 10 power 5 plus, right? So somewhere here after like before 10 power 5, we have here -2. We're going to add this number here. Yeah. Did you understand this? And for -3, where do you do it? Is here. -1, -2, -3. By adding this 10 power 5, you can make this the negative number a positive. Like you can store it in a positive index. And 10 power 5 represents here, like -10 power 5 is equivalent to 0 in this case, index 0. Yeah. So if you understand this, have it, give a thumbs up. If you didn't understand, you can give a thumbs up, thumbs down. Hello. Yeah. Sorry, I was in mute. Now let's take this array. Let's not just not think about these negative numbers. Let's just take this array. How do we count these numbers? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, yeah, 10. So yeah, now for 2, where do you will initialize this everything with zeros at the start of the starting? Then we'll start from this. The starting, when you go to 2, what we do is we increment uh, the count here. Okay, after that, after going to this 2, we increment the count like this, then 1, we increment the count of 1 here. And how do you do this? How do you do this is frequency of 2 plus plus. Yeah. Then again frequency of 2 plus plus. Yeah. So doing this, you can increase the count of this particular number using the index. Then again 5, for 5 we can increase the count here, 1, 2, 3. Okay, then 6 here, 1, 2, yeah, 7 here, 1, and 1 we get, yeah, 2. So this array represents the frequency of every element or integer that is present in this. The frequency array represents every count of this array here present here. So now after using this, we can just output the frequency of every number using a for loop. Okay, I has frequency of I. Yeah. So if you understand this, have a thumbs up. Okay. Okay. Now let's like I yeah, I gave you this constraint, right? I from 0 I less than or equals to 10 power 5. What do you do here is we initialize an array of size. How much can I tell me what's the size of this array? What should be the size of the array be in the chat? Yeah, if you understood this question, if you didn't understand this question, give a thumbs down. Yeah, you can do that also, but if you want, if you have to do it using an array, you can do that in that way also, using two arrays where you count the frequency of positive numbers in one array and the negative numbers in another array. But using a single array can, help you, uh, it makes it easy instead of using two arrays, like knowing where the negative number is, knowing where the positive number is. Okay. Yeah. Just give me the size of the array. What should be the size of array for these constraints? The size of the frequency array. Yeah, good. So the size of the frequency array should be 10 power 5 plus 1, because the indexing starts from 0. If you give 10 power 5, the array size would be 10 power 5, but the last index would be 10 power 5 minus 1. So to initialize, to give the size of the array to be 10 power 5, the last index to be 10 power 5, we should give it as 10 power 5 plus 1, so that the last index is 10 power 5. Yeah. If you understood it, give a thumbs up. Yeah. Okay. So this is how you initialize a frequency array, and to have the count of the numbers in it, you just increase the frequency as like index a of I plus plus. Now here, every time if you have an array, integer array, if you are given an array, you don't have to initialize it with 10 power 5, right? If you are given an array like 3, 2, 4, 6,000 and 2, watch, like for this array, frequency array, what should be the minimum size, so that you can like count the frequency of every number in this array. So if you understood this question, give thumbs up. Yeah. What should be the size of this frequency array for this given integer array A? Yeah. So it should be 1001, because the maximum element is 1000. So there's no need of going till 10 power 5, right? Right. If you understood this, give thumbs up. Yeah. So while initializing this frequency array, what you can do is you can initialize it with maximum of this array plus 1. Understood? So there's no need of initializing the array with 10 power 5. Okay. So if you understood this, give thumbs up. Yeah. Okay. We'll add on some more constraints, like I gave it to you before. Like we have an array which consists of negative numbers also, like from 10 power minus 5 to 10 power 5. So how do you count the frequency of all the elements in this array? Using a single frequency array. Yeah. So yes, doubling the size of the array. Okay, that's great. Let's take an example here. Example like -5, -2, 1, 4, 3, 2, 0, 6. So in this case, what we can do is instead of taking array till minus doubling the array into have an array with size 2 into 10 power 5, right? So where can we store this -5? We want this -5 at the 0th position. Like this is the least number present in this array, the negative number, right? So we need to store this at the 0th index, right? So here, what we can do is can just add the numbers with the least number. If it's a negative number, we can add it with the least number. That is -5. So -5 when you add it with 5, so it becomes 0, right? There you can increase the frequency of the number. So -5 here at the 0th position it becomes 1. -2, what does it become? Where where do you store the frequency of -2? Yeah. If you understood this question, give a thumbs up. Like if you didn't understand it, you can give a thumbs down. Okay. So where do you store this -2 in this frequency array? Given that you're adding 5. Yeah. 3. So we store it. So let's take here representative -3 -2. So we store -2 at third index. 1, where to store 1? Yeah. 1 at the sixth index, and so on. So that's how you do it with the negative numbers. Now, given that you have a negative number like -10 power 5, what you do here is you just add this like the minimum element, the minimum that you get from the negative numbers. If it's any number, like if it's -10 power -100, you add 100. Okay. So that's how you do this with negative numbers. Yeah. So using this frequency arrays, we can constrain the time to O of n and also space to O of n, right? So if you understood till here, just give a thumbs up. Yeah. I'll ask you another question. Uh, Given to strings, I want you to find if they're anagrams or not. What are anagrams are? Like if you rearrange a string, you can form the similar string. Like example, A, B, C, D. Then you have this string 1. Then you have other string C, D, A, B. Okay, this string 2. After reforming this, you can make this into the string A, string 1, right? So I want you to find if this given two strings, I want you to find if these two strings are anagrams or not. Yeah. If you have an approach, you can just put it in the chat. Yeah. Did you understand this question? If yes, give a thumbs up. Yeah. So what an anagram is, after rearranging the string to string any string, you can form the string one. Yeah, I'll take another example like ax c f f string one. Then we have f a x c f string two. These both are anagrams. Yeah. Coming to this a b c, then c b d. These both are not anagrams. Yeah. Did you understand what anagrams are? No. Give a thumbs up for yes. Yeah. So some of you said that sorting both of them. Yeah. You. What do you think the complexity of sorting is? Sorting anything, a string or a integer array is. What is the complexity of sorting? Yes. Yeah. So you're doing it in log n. Yeah, that's a good approach. But you can just have a frequency array, right? Can what you need to do is for anagrams is you have to check if all the characters have the same frequency or not for the both strings. Yes or no? If you understood this, give thumbs up. Yeah. So how do you store the frequency of these characters in a frequency array? Uh, how do you store this frequency of these characters like A, B, C, D? These are not like numbers, right? They don't have index, proper index to store them. So where are you going to store this A, B, C, D? Yeah. So tell me what's the ASCII value of A? What's the ASCII value of A? Small a. Yeah. Yeah. It's 97. Yeah. Good. So what you can do is here, whatever character you have, let's say you have a character char ch. How do you store the like how do you increment the count of this character? Sure. What do you fill here in the frequency? Sorry, do you understand the question? Yeah. If you understood this, like what do I ask you? Just give a thumbs up. Yeah. So how are you going to store this character A's frequency in this frequency array? You're saying that yeah, the ASCII value of A is 97. Okay. Then how are you going to store this? So how do you do it is like we know that int of this character. Yeah. int of this character gives you the ASCII value of this number of this character, right? So one method is, what you can do is like int of character minus 97 plus plus. So for this, you can store the frequency of a character a at the 0th index, right? Like a's 0th index means that you're storing a, right? Yeah, if you understood this, give a thumbs up. Yeah. So that's a method. This another method, you can also do it like the frequency of this character minus plus plus. So what does this do is, you'll get the integer value of the character by using this. Okay. When you do this for a, what do you get? What does this mean? What do you get by doing this? What's the value after yeah, after doing this operation? If you know the answer, put it in the chat. So what do you get this value as? ASCII of character minus 97. What is the value of that? Like here, what is this represent? So yeah, so this represents as 0. When you do this, we get an integer value 0, right? Yeah. How many of you understood this? Give thumbs up if you understood this. How do you get 0 after doing this operation? Did you understand this? Yeah. So what do you do is, you can just store the frequencies of this string 1, string a, you're giving string 1, s1 and s2. So what do you do is, you initialize in frequency array. What should be the frequency array size? What should be the size of frequency array? 24. Yeah, 26. It should be 26. So now, how are you storing this? The frequency of every character from S1 and S2 in this frequency arrays. Write the code if you can in this chat. Some of you are telling 52. Why 52? Okay, you're saying that you have small and capital letters. Okay. Now I have A in this array. Let's say I have A. What will A capital A minus small a be? What will capital A minus small a be? 26. Yeah, we'll get a negative value minus 32. What's the ASCII value of capital A? It's 65, right? Small a, it's 97, right? So we'll get 32 as a, we'll get 32 minus 32. This we can't store in the frequency array, right? So how are you going to handle this? Just think, you know that if just look at these characters, if they're all these characters, after rearranging them, you can make them equal or not. Just no need of checking if they're capital or no, right? Right? Did you understand this? If you understood this, give thumbs up. This no need of checking if it's capital or small, right? Yeah. So what we can do is this no need of like it's a, again counting how many capital A's are there. Just what we can do is if it's capital A, we can just turn it into a small a, right? How do you do this? How can you change capital A into small a? Yeah, yeah, plus 32, 2 lower, yeah, great. So what we can do is before this frequency array, you can just two lower all this or to lower all this characters in S1 and S2, right? I guess there's no need of again I mean explaining what's too lower and these all things, right? You know what are these? If yes, give thumbs up. Yeah. So we do after that, after lowering all these characters from S1 and S2, what we do is just increase the frequency of get the frequency of string 1 and string 2, right? So yeah, S1 of I minus A plus plus. Yeah. Did you understand this? How many of you understood here this code? If you understood this, give a thumbs up. Yeah, you do the same thing for the frequency array B, the S2. After that, how do you equate like how do you know this how do you know this both S1 and S2 are anagrams? After doing this, you get the frequency array of S1 and also the S2. How do you say that they are anagrams? Yeah, you can just write it down in the chat. How do you say that those both are anagrams or not? S1 and S2. If you understand this question, just give a thumbs up. Do you understand the question? Yeah. So the frequency of every character should be same, right? So what you have to do is just check the frequency of every character. The for loop runs from I 0 to 26, right? Then if frequency of S1 is S1 of I, it's not equals to frequency of S2, then we break here or we return false, right? And if everything is equal, we can just return true, right? Did you understand this? If you understood this, give thumbs up. Yeah. So this is how you count the frequencies of string, and you can also check if they're anagrams or not. Okay. So we are good with all these topics, right? Whatever I covered till now. If you have any doubt, you can post it in the chat. So if you understood this, give a thumbs up. Okay. The next topic will be taken over by Nandan.
So, hello everyone. I'm audible, right? Okay. Myself and Nandan. I'll be taking up 2 pointers. So there are two ways. So there are two variations in 2 pointer. Like one is we have a slow and fast pointer, and then we have a front and back pointer. So the first one we generally use in while we are dealing with linked lists, and the second one, they you'll not see many questions that will be directly asked on 2 pointers, but this variation is quite used with some other approaches. So we'll see some questions on this. So you'll be given an array of size n, and you need to find a pair of numbers at some indexes I and j, such that the sum of them, like array of I plus array of j, equals to some number k. You'll be given with this number k. Uh, for example, array is 10, 20, 35, 30, 40, let's say, and k is equals to 50. So can you manually say the answer is yes or no? You just need to say that whether a pair exists or not. Um, and also mentioning that you cannot reuse the number, like I should not be equals to j. So is the question clear, everyone? So I can manually see that 20 plus 30. So index is 1 and index is 3. Array of 1 is 20 and array of 3 is 30. We found a pair I comma j such that I not equals to j and given k is 50 and it's equals to 50. So we found a pair. So we return true. Uh, and for other k value, let's say k equals to 65. Is it possible? Mention in the chat. Okay, 35 plus 30 equals 65. It's possible as well, right? Let's say 61. It's not possible. So any approaches for this question? Obviously, there's a brute force solution. We iterate in the first for loop. We iterate from I is equals to 0 to n. In the second for loop, we iterate from j equals to I plus 1 to n. And then you check here if at any point of time if array of I plus array of j is equals to k, then you return true, and after ending of both the for loops you return false. This is true. I hope everyone is comfortable with this approach. What's the time complexity of this approach? Mhm. So it's big of n square as there are two loops. One is running from 0 to n. Big of n square. So let's take the same array 10, 20, 35. Okay. 10, 20, 30, 35. Let's say 50. So we'll initially sort this array. Assume that you are giving some random array. I initially sort the array. So I've taken a sorted array. We'll take two pointers. Let's say the pointer is I and one pointer is j. I is pointing at the start, that is at the index 0, and j is at pointing at the last index. This is index 0, 1, 2, 3, and 4. Okay. We call this as front and a back or I or j, anything is fine. I'll be calling it as I and j. I'll tell you the logic first. So we check if array of I plus array of j equals to k or not. Assume that k equals to 50. So when I equals to 0 and j equals to 4, what's the value? 10 plus 50, which is equals to 60. But that's not equal to our required k value. This is in fact greater than our k value, right? Did you understand till here? Okay. So what are we supposed to do? We are getting some value which is greater than the expected value. What needs to be done? So somehow we are considering a value which is greater. We have initially sorted the array. So our array values are always increasing. So we wanted to reduce the value. So we decrement our j, decrementing j. So initially j was at 4. Now we decremented it. So now j is pointing at index 3. So I still remains pointing at 0 and j points to 3. So now array of I plus array of j, what does it become? 10 plus 35. 10 plus 35 becomes 45, which is less than 50. So based on the previously or previous problem, previous case, what should we do in this case? We got a value that is less than 50. We somehow need to increase our value, right? Choosing the I and j, we need to increase. And we initially sorted the array. So which pointer should be moved based on the previous discussion? Can you mention in the chart? Okay, I. Should I increment the I or should I decrement the I? We increment the I, right? To increase the sum, we increment it. So now I is pointing to index 1. So now I equals to 1 and j remains still at 3. And we check array of I plus array of j uh, is equals to or given k or not. We usually compare, not just finding if it's equal or not. We see if it's greater than or it's less than or equals to. It's coming as 55, which is greater than 50. This step is similar to our first step, right? We somehow saw our sum is greater than our expected k value. So what we do? We again increment j. We continue the same process. So now we decrement j. What happens? J points to 2. Now our I is at index 1, j is at index 2. Array of 1 plus array of 2, what it becomes? 20 plus 30 equals to 50. 50 is our required answer. We simply return true. Clear till this point? Okay. So we initialize I equals to 0, j equals to n minus 1, and then we do while I not equals to j, you check if array of I plus array of j equals k. What if it's equals to k? We simply return true. Else if array of I plus array of j, what if it's greater than k? Greater than k means our sum is greater than the given k value. You, what should be done at this step? Else what should be done at this step? Consider this 1 and consider this 2. Mention in the chart what you need to write at place 1 and what you need to write at place 2. Okay. At 1 you write j minus minus. At 2 you do I plus plus simply. Clear till now? And at the end, if you did not found any fail, return simply return false. And before doing any of these steps, you have to sort the array. Ensure if it's a given array is sorted, it's okay, but you need to sort the array. This takes log n time, and this takes n time, and log n time. Sorry. So overall complexity becomes log n. Clear with this problem, or should I repeat any of the steps? So I've sent a link to the. So guys, spend a minute and try understanding the question. There are n children who wants to go to a Ferris wheel, and your task is to find a gondola for each child. Let's say this Ferris wheel is a giant wheel, and this gondola is a box in the giant wheel, and there are n children. Each box may have one or two children in it. What does this mean? The box is not left empty, and box at max can have two children, either one or two. It cannot have three. And in addition, the total weight uh, may not exceed x. So when he means the total weight in a gondola may not exceed x, the weight of every child. What is minimum number of boxes needed for the children? You are given n and x as input, and then the next line n contains n integers, the weights of each children. So for the sample, n equals to 4 represents 4 children, and x is 10. What does this x represent? It's the maximum, the total weight in a box, and 7239 are the weights of the children. Okay. So in the sample 410, so n equals to 10 and n equals to 4 and x equals to 10. Seven to 39. And the weights of the children are 7, 2, 3, and 9. So let's manually find out the answer for this. We can give child with weight 9 one box, child with 7 as one box, child with 2 and 3 as one box. Okay, now let's see in box 1, the weight of the children is 9. In box 2, the weight of the children is 5. In the box 3, weight of the children is 7. In all the cases, it's always less than or equals to 10. We are not exceeding 10. This could be one way, or any other way is possible. 7, 2, 3, 9. You can give one box to child 9. You can give one box to 7 and 2. Give one box to 3. Any other way? You can give one box to child 7 and 3. You can give one box to child 2. You can give one box to child 9. These are the three ways. Any other ways possible? At least did you understand the this test case? Do you understand the problem and this test case? So any way of approaching the problem? Mention in the chat, anyone? All the children needs to be accommodated in the boxes, and each box should not exceed the given x weight. Okay, no one seems to have an approach. Did you see that we cannot club this child with weight 9 with any of the others? in this example. Why is that so? If we club 9 with 3, it becomes 12, which is greater than 10. If we club 9 with 2, it becomes 11, which is greater than 10. Similarly with 9 with 7. So what we do is, we initially sort the given weights of the children. So sorting it becomes 2, 3, 7, and 9. Or this becomes our array. Now we just do implement the two pointer approach. We have one pointer at the front, we have one pointer at the back. Let's say they are I and j. And initially we initialize our required boxes to 0. Initially we assume that no boxes are required and we take two pointer. As we see, we can accommodate either one or two children in a box. So let's consider, if we'll try to consider, we take two children in a box. Let's say we want to consider 2 and 9, these two weights in one box. Is it possible to accommodate 2 comma 2 and 9 in a box? It becomes 11. We cannot accommodate. So we try to accommodate the maximum value, that is 9. We can only accommodate 9 in this box. So we'll give a separate box for 9 and we decrement the j pointer and increment our boxes to 1. So one box is given to 9. Now let's see if we can give a box to 7 comma 2. Can we do that? Mention in the chart. I is pointing to 2, j is pointing to 7. These are the children with weights 2 and 7. We create a new box. Can we keep 2 comma 7 in this box? Yes, we can assign, because it's the total weight is still less than 10, less than or equals to 10. So we can accommodate. So we move our I to I plus plus and decrement our j. Because we have explored this 2 and 7, we have kept them in our boxes and we do increment our boxes count. Now our I and j is pointing to 3. And we can keep him in one more box. This is less than or equals to 10. This is also less than or equals to 10. We have did not violate any of the conditions, and we accommodated all the children, and each box contain either one or two children. So the main logic here is, we need to sort the given weights of the children. Based on the sort, we first need to accommodate the children with maximum weight. We first try to see whether we can accommodate one maximum plus one minimum. If it's not possible, we try to accommodate the maximum person in one box and decrement the j pointer. Are you clear with the approach? This is a slight variation of the two pointer approach. I don't see any responses from your end. Is this explanation clear, or we wanted to trace it from any other example? So how the code looks like? We initially sort the given array, initialize I equal to 0, j equals n minus 1, and then you do while I less than or equals to j. If array of I plus array of j, this represents the weight of the children. If they are less than or equals to x, what does this mean? We can accommodate both of them in a box. We do boxes plus plus. Initially, write take boxes equals to 0. And then if we can accommodate both of them in a box, we do boxes plus plus, and we move forward to the next child in the front pointer as well as the back pointer j. We decrement this because we have considered both of them. Else, can anyone help me here? What do we write in the else block? Else we need to increment our boxes and do j minus minus. Why so? In the case we had 9, 9 plus 2 is 11, which is greater than 10. We cannot accommodate two children in the same box. So we consider we'll keep 9 in one box and decrement our j pointer. So we'll keep 9 in the box. In code, we take new box, that is incrementing the boxes one, and then we decrement j. So the j will point to 7. That's the code. At the end, you return the number of boxes. Simple. So these are the two problems that only use two pointers. There's no other concept involved in it. Sorting plus two pointer. In general, a mixture of problems can be like we have binary search plus two pointer, or a sliding window with two pointer. A mix of these questions can be possible. For now, I just wanted to introduce you to two pointers. So we just thought the concept. And let's move on to the next one. Let's suppose say, guys, can you mention in the chart what's the maximum value the int can store, the int data type? Okay. Not so many responses. Okay, the range of integer is minus 2 power 31 to 2 power 31 minus 1, right? You see this? So in problems, you are supposed you are given a number and you need to find the factorial of a given number. Let's say given. You know how to find it for 5, it's 120. You just loop on from 1 to 5, you multiply and then print the results. Let's suppose say you wanted to find factorial of 20. Is it possible in the int data type? You need to multiply 1 into 2 into 3 into 4 till so on 19 into 20. Will this fit in the integer data type? So this will not fit in the int data type. Even if you take long, for long, factorial of 20 will fit, but factorial of 21 will not fit. It will overflow. Let's suppose say uh, uh, the range of integer is minus 4 to 4. Assume that the range of integer is minus 4 to 4. So how does it look like is minus 4, 0, 1, 2, 3, 4, minus. It looks like something like this. So when it crosses 4, it goes to, sorry, 7. So we have 0, 1, 2, 3, 4. After 4, it will goes to -5, -4, -3, 2, -1, 0. So if the maximum value that we can accommodate is 4, after 4, if you try to add 1, it becomes negative due to the integer overflow in any language. So in order to handle this, we have something like modulo. In many of the questions, you would have seen that print answer modulo m. What does this do? This the final result after taking modulo will lie between 0 to m minus 1. Let's say take some examples. Suppose say m equals to 5. If we try to do 24 mod 5, what's the answer? You get 4. Let's say 21 mod 5, you get 1. 25 mod 5, you get 0. The answer always lies between 0 to 4, right? That is 0 to m minus 1. So we are restricting the range of this input by taking mod m. So in many of the questions, when there is a huge multiplication involved with large numbers, or multiple times you are adding something to a large numbers, they usually try to give take mod m at every step. So there are some basic formulas to remember in while dealing with modular arithmetic. Let's suppose say a plus b mod m. It's a mod m plus b mod m, and we need to take whole mod m. Let's take the example 2 plus 4 mod 5. Let's say mod 5. Manually it's 6 mod 5 and it's equals to 1. Using the formula, it's 2 mod 5 plus 4 mod 5 whole mod 5. What is 2 mod 5? It's 2. 4 mod 5 it's 4 and whole mod 5. It gives the same one. Did you get this? So we'll take one more example. We'll take 10 plus 6 mod 5. We write 10 mod 5 plus 6 mod 5 whole we take mod 5. So what does this become? It becomes 1, right? Similarly, we have formulas for subtraction and multiplication as well. I'll quickly write them here. A minus b mod m is a mod m minus b mod m plus m whole mod m. So this plus m is to handle the negative values. Let's suppose say a is 4 and b is 6. So some m maybe 2. So 4 minus 6 becomes minus 2 mod 2. So there is no modular arithmetic defined for negative values. So we add plus m. When we add plus m for minus 2, we add plus 2. Let's say m is 3. M equals to 3. We add m plus 3. It becomes 1, and then we take mod with 3. So adding plus m doesn't change the mod value, resultant mod value. Similarly, for a into b whole mod m, it's similar to the case in addition, a mod m into b mod m whole mod m. So if we are given something like 10 power 12 into 10 power 6 or 8, 10 power 8, while doing this multiplication, the we cannot store the resultant value directly. So 10 power 12 can be stored in long, and 10 power 8 can be stored in long. While multiplying these terms, if you take mod with, let's say, some m, and mod with, say, let's say, some m, and whole with let's say m, this mod generally will be 10 power 9 plus 7. I'll let you know why it will be generally 10 power 9 plus 7 in a minute. Assume that so this value will be less than or equal to 10 power 9 plus 7, this one as well, and the whole resultant will be less than or less than 10 power 9 plus 7. So in programming context, you'll be seeing usually as 1e9 plus 7. It's same as 10 power 9 plus 7. So the first reason is it's a prime number. The second reason is it's close to int max. It's in the integer range, and it's close to integer maximum value. And being it a prime, will there won't be any other collisions as such. Like suppose say we'll take 16. 16 mod 2 is 0. 16 mod 4 is 0. 16 mod 8 is 0. So for multiple taking mod with multiple values, we are getting the same result. But if it's a prime number as such, 16 mod 3, we'll get some unique value. And if it prime number is large enough, the value might be unique. So the collisions will be decreased. So the answer will be unique, to be more precise. So usually m will be given as 1 in 9 plus 7, and you need to take modular into consideration only if it's mentioned in the problem statement. Otherwise you can carry on with the normal flows and steps. Otherwise you need to implement the modular. Just to familiarize yourself with modular, we have discussed these topics. If you did not understand this part, it's okay. Just for now, remember the part addition formula, subtraction formula, and multiplication formula. And if you have time, uh, explore about what can be written here. Do check out. It's based on Fermat's little theorem, which requires a calculation of B inverse. I'll leave this for you. If interested, you can explore. Uh, right, we are closing the session. We are done for today. We explored about space complexities, time complexities, sortings, frequency arrays, two pointers, bit manipulation, and any other topics as well. So I'll hand over to Shrikar. He'll conclude the session.
Yeah, so if there are if you have any doubts that you have regarding competitive programming or whatever, you can basically ask us right now. But before that, I will actually tell you these are like the very basic topics that we've covered right now. These are very simple and basic topics that you absolutely need to know to start off competitive programming. But then to people who have actually started competitive programming, I would ask you the one thing that I would like to tell you is if you have, you definitely will have to give contests in code chef and code forces. Like code forces is like definite, you should like definitely touch code forces. You always you have to give contests on code forces. This is the must that you that should do. And of course you need to do coach of contest as well. They're equally good. And also I would definitely like you to check out this thing called the CSES problem set, right? Because that is like very helpful in the introductory problems and searching problems. They're really nice, right? So we could cover what we could cover what we could in these 2 days. It is like very tough on our part also to discuss all the problems. We could do what is in our hands. But then if you have any doubts regarding competitive programming, or if you guys have doubts regarding any topic, or how to do stuff and stuff, like you can contact us through I mean you Yeah, that Turing Hut workshop group is there, right? Like the WhatsApp group. You can find everyone's number there. Like our team is entirely over there. You can post a message in the group, or probably DM one of the team members if you want help. We will definitely be more than happy to help you out. So that's that. And more important topics that we did not cover in this session, and probably which are like kind of hard to master and stuff, are dynamic programming. We did not cover dynamic programming, graphs, and trees. These are like yeah, recursion, of course. No, you guys must be feeling like, what is recursion? I mean, isn't recursion basically just towers of Hanoi? It's not. It's very much more than that. I don't think towers of Hanoi is probably taught to you in the curriculum. It's like very deep stuff, right? If possible, we'll be taking another deeper session on recursion and possibly dynamic programming if time helps. But then for now, it probably is not possible. Right. So, what I want you to do is firstly get down and solve these basic problems. And also, I'd like to add binary search to this. Like, one common misconception that people have is binary search is only used to search an element in the array, which is totally wrong. Binary search is much more than that. And it is, like, I would say, the most important topic in the entire competitive programming thing. Like in the entire, say, easier side of competitive programming, binary search is like very important topic. And if time permits, probably check it out on your own, right? uh, yeah, if time permits, please check it out on your own. And one more thing, yeah, if you have any doubts, please contact us. These sessions, both these lead code, look, the thing is, if you just want to do DSA, lead code is more than enough. But if you want to get into depths of competitive programming, you need not do code forces or anything. If you really want, like, if the thing is, CP, if people do CP, the majority of people do CP because they're interested. It's not like it's not really to crack a company or learn DSA, right? So if you just want to put your concentration into DSA, you can just basically do lead code or interview bit or whatever, learn solve the drivers as D sheet or whatever. That will be more than enough. You do not have to give grind code chef or code forces or whatever. If you want to do DSA, that is another path. But if you really want to get into the depths of CP, then code chef, code forces, everything comes into picture. That's that. So I do Fang ask CP questions. Hmm. I would say no. I guess even for Fang, if you do like normal, ask questions, in the sense, I'm talking about interview perspective or online assessment. Sorry, see, the thing is, for Fang thing, there are two parts. Okay, first thing, there is an online assessment that is conducted, and second thing, there is like on-site interviews, right? For online assessment, probably you will have some medium level CP questions, medium level competitive programming questions, asking from probably from dynamic programming like DP, or graphs or trees or binary search, or something like this. You have medium level CP questions, not even hard. For on-site questions, they're like literally just medium level DSA questions, not even CP. If you are good at CP, both of these rounds are literally a cakewalk for you. So if you do like medium level DSA questions, that is enough for on-site rounds. And to get to the on-site rounds, you need to do some good DSA. Very good. I would say very good DSA. I hope that answers your question. Does anyone have any other question? Contest? Oh, we oh yeah. One more thing. You have a contest at 3 p.m. a practice contest. Basically, you don't. I mean, the leaderboard is not taken into consideration. We'll share the link at 2 p.m. and the contest is like from 3 p.m. to 5 p.m. By 2 p.m. we'll be sharing you the contest link. You can attempt it then, like at 3 p.m. Any other questions? So yeah, if you do have any other questions, please reach out to us on the group or maybe personally. So that's been from our side. Thank you very much for. Oh, sorry. Is lead code sufficient to clear these 2 rounds? Yeah, I would say yeah. It's more than enough. I mean, do a little CP also maybe. Touch a little CP. If you're doing so much lead code, do some CP and go, so that it helps you in this online round. On-site round questions are rather very easy, I'd say, in FANG. Like medium level DSA questions would be more than enough for on-site rounds. For online assessment, maybe touch some CP so that it helps you. Like, yeah. And yeah, I mean, building up CP profiles on Codeforces and CodeChef is also going to help you get your resume shortlisted for the online round. Yeah, so that's been from our side. Thank you very much for participating. We'll see you in the next event.